Swayam Prabha. Digital India. Educated India.
Good morning, this is lecture number 32, the last lecture in this module 5 on matrix analysis of beams and grids. So we will be completing 6 sessions on this module. The remaining topic is application of matrix analysis to grids, and we will be applying stiffness methods. As you know, the grid element is different from the beam element in that you have an additional degree of freedom. You have the angle of twist, and the corresponding force is the twisting moment or torsion. This is covered in the chapter on beams and grids in the book. So let us quickly review what a grid is. I have given you a segment of a grid. You have 2 interconnected beams monolithically connected at the joint B. If you separate out the 3 free bodies, you will find that there will be twisting in all 3 of them, and at if we say A, C and D are fully fixed against both flexure and torsion, then you have only 3 active coordinates at B. You have a vertical translation, and you have rotation about 2 axes as shown in that figure. If you take out the free bodies, you will find that in addition to shear and bending, you have a twisting moment. The twisting moment at the 2 ends of each element will be equal and opposite, as there are no intermediate twisting moments. If you treat the beam CD as one beam, then you would have to put a torque at B, but if you separate out the 2 elements, they would look like this. Compatibility demands that the rotations at B should be the same for all. What would be flexural rotation for one beam would turn out to be an angle of twist for the perpendicular beam, and equilibrium has to be satisfied at that location B. The resultant force should add up to whatever force acts at B. So in general, these are fundamental concepts. Okay, how do we address these issues in matrix analysis? If you recall, we had covered grids in the force method of analysis. We had actually applied the method of consistent deformation, and we had also used the theorem of least work. In that, we had actually separated out the beam elements and put some equivalent springs and try to solve the problem in that manner. But that is not effective if you have large grids. So it is better to deal with the whole grid structure in one go, which is possible in a matrix framework, and we will be looking only at the stiffness method of analysis. So there is something called a torsional stiffness for a grid element, which is what you get in a shaft. If a shaft, let us say a circular shaft, solid circular shaft or cylindrical shaft, is fixed at one end and you apply a constant torque at the other end, then the angle of twist is given by Gj by L times the torque that you apply. So we can talk of a torsional stiffness Gj by L. G is the shear modulus, J is the polar moment of inertia, L is the length of the element. It is in many ways similar to axial stiffness, Ea by L. It also has vectorially the same direction, except that you will use a double arrowhead. It is important to note that this concept of polar moment of inertia is strictly applicable only to circular sections, cylindrical sections. They could be solid or annular. The reason is, in other sections, in non-circular sections, you are likely to encounter warping, okay, longitudinal movements which needs a separate treatment. Now even if you are having, so let us take a look at the two perfect circular sections. The polar moment of inertia formulas are very well known. The relationship between shear modulus and elastic modulus in terms of Poisson's ratio is also well known. If you are dealing with a non-circular section, then the presence of warping complicates the derivation of torsional stiffness. However, in cases where there is no restraint against warping, we can still use Gj by L, but J is not the polar moment of inertia. J is called an equivalent torsion constant, sometimes denoted with the symbol C, but let us stick to J. It is also called Saint-Venant's constant because it is Saint-Venant's torsion. If there is warping, you have to slightly modify these terms. Okay, so let us take the simple cases of no warping. If so, in a rectangular section, the value of J can be shown to be as shown in that expression. If you, it's a function of B and D. B is the width of the section, D is the depth of the section, B is assumed to be less than D, otherwise you have to interchange the terms. And the shear flow is as shown in that picture. If it is subject to a clockwise torque, the shear stress is 0 at the four corners, though the distances are maximum from the center. That is because of complementary shear requirements. If you are dealing with a narrow rectangular section, then that formula reduces to a very simple formula, B cube by D, B cube D by 3. That is when it is infinitely long. This is an easy formula to remember, and for thin walled open sections we can just use this formula and add up different segments. Okay. For example, I have shown here two thin walled sections. The one on the left, the I section, you can derive the formula using the formula for the narrow rectangular section because it is an open section. The one on the right, however, is different. It's like the annular section, annular tubular section, except that it's a box section. It's commonly used in bridges. It's very good against torsion. The reason why this section is very effective against torsion is if you look at the nature of the shear flow. You'll see that in the case of the I section, the lever arm for the shear flow is very small, so you don't get much resultant torque, and so you get a large twist as well. But in the case of a box, you have a constant shear stress across the thickness of the wall. It's like a circular section, so it's very effective against torsion. Okay, that's because it's closed. If you cut that box anywhere and make a slit, then it's not effective, as effective. And for if you have a slit, you can go back and use the formula for a narrow rectangular section and add up for the different segments. Anyway, these formulas are available if you want to use them in practice. Let's look at simple problems like this. Okay, this is a grid problem which we will try to solve. We've shown here for convenience 6 by 2, 3 by 2 grid, but you could use it for any large grid as well. The grid element in the conventional stiffness method will have 6 degrees of freedom. It's just like the beam element, except we have an additional, not axial, torsional degree of freedom at both the ends. So we have 1 star, 2 star, 3 star. The 3 star we reserve for the torsional, the angle of twist. Similarly 4 star, 5 star, 6 star. The element is assumed to be prismatic with a flexural rigidity EI, constant flexural rigidity EI, and a constant torsional rigidity GJ. Later in the next module we will look at the more complex space frame element, where you have to add one more a plane frame element, where you have to bring in EA, axial rigidity. If it's space frame, you have to bring out some more quantities which makes it more complex. But this is a spatial structure because the loads are acting perpendicular to the plane of the grid, and in general the axes in the global Cartesian coordinates will not be the same as the one for the local coordinates. So you have theta, it is actually a rotation by the angle theta in the xz horizontal plane, and we will see how to derive the displacement transformation matrix for such a situation. Please note, grids do not necessarily have to be orthogonal, we will see examples where they could have any orientation, and if you want to do the reduced stiffness method, that 6 degree of freedom model will simplify to how many degrees? 3, because you will find that the rank of the stiffness matrix is only 3, and to make it stable you have to give 3 supports. So we will look at this later. Yes? X and Z are X, Y and Z are global. Okay, I have marked it there. X star, Y star, Z star are local as per our standard convention. X and X star need not be in the same direction like in a beam, like in a continuous beam, right. In this orthogonal grid problem, it will be either 0 degrees or 90 degrees, right. Have you got it? So, but in general it could be 45 degrees, 30 degrees, any angle. Is it clear? So I am doing a generic formulation, but please note, if X and X star are separated by an angle theta, then Z and Z star are also separated by exactly the same angle, because it is just a rotation about the horizontal plane, and Y star are identical because the vertical, the normal to the horizontal plane is the same. Okay. Okay, let us look at this more carefully. We will look first at the conventional stiffness method. This is the element we were talking about. The element stiffness matrix is simple if we make a basic assumption that the torsional stiffness component and the flexural stiffness components have no interdependence. Okay, that is a convenient assumption we are making here. So you remember we did we looked at the plane frame element, we are going to look at it in detail in the next module. So you will have this Gj by Ei coming here, you will have 0 0 here, 0 0 here, because this is your torsional constant. It should be actually Gj by L, but for convenience if I take Ei by L outside, I have to write here Gj by L. Please note that if this is Gj, then this will be minus Gj, and so on and so forth. The diagonal elements will be always positive. The rest of the matrix is exactly what you had for the beam element. Remember, for a beam element we had 12 Ei by L squared, 6 Ei by L, and so on and so forth. So we have added just 2 rows and 2 columns, 2 additional rows and columns at the right places, because 3 star and 6 star come at the end of each of these coordinate numbers. Is this clear? It is not difficult to derive, it is just a superposition of torsional stiffness to your beam element stiffness diagram. There is no other change. We have added the third row, the third column, the 6th row and the 6th column, all of them are 0 except the diagonal terms and the corresponding terms at the other end. The diagonal terms will be positive, the other terms will be negative. Okay. So let us see how to deal with the lack of alignment between the local coordinates and global coordinates. So you have a difference between x star and x, and it is easy to write down because you remember we have done this earlier in the case of a truss. So it is a similar kind of rotation we are doing, except that now we are doing it in the horizontal plane. Okay, we are doing it in the horizontal plane. D1 does not change because that is a translation in the vertical plane, it is in the y direction, right. So D1 does not change, so you have 1 there, and the rest of the transformation comes from your rotation, and so it follows a familiar pattern, cos theta minus sin theta cos theta. I hope this is not difficult for you. We have done this kind of transformation earlier, we are doing it exactly the same way. It is very easy to remember and we need to apply it. But fortunately for you, we are not really going to solve any problems by the conventional stiffness method because it takes a lot of time. We will however try to solve the problems more conveniently by the reduced element stiffness method. So conventional stiffness method is the same. In the book on advanced structural analysis there are some problems solved, but we will not attempt those here. We will go straight away to the, so this is conventional stiffness method, we will go to the reduced element stiffness method. Here the transformations are much easier to do. Let us look at that. So now we are dealing with a 3 degree of freedom system, 1 star, 2 star and 3 star. The 3 star is the new addition that you have over the beam element, right, and the direction of it is pointing outward. It is a double arrow head and you need to give it a new interpretation. Earlier remember when we had the axial element we had a single arrow pointing outward. The understanding was if it is D1 star it refers to an elongation in the element. So if there is an elongation it is positive, if there is a contraction it is negative, and we also had F1 star for the axial element. If it is positive it means there is axial tension, if it is negative it means axial compression. You need to have something similar here for the torsional degree of freedom. So this is how we interpret it. As a sign convention we shall assume twisting moments and angles of twist to be positive when the corresponding vectors shown with the double headed arrow at the ends of the element are directed outward along the longitudinal axis. This is consistent with the earlier sign convention for a single headed arrow for the truss element. Is it clear? So just remember this, you will understand when we do it in an application. Okay. Now it is not always that you need to apply grid elements in a grid problem. You can replace some of the grid elements with a simpler beam element. Can you tell me where you have these opportunities? When there is no torsion, when is there no torsion?
When there is no
When can you release torsion?
Torsional stiffnesses.
Well, there are two instances. The first is when you have symmetry. If you have symmetry in the system, you might find that to satisfy symmetry in some of the beam elements you cannot have any angle of twist. So you know for that particular loading condition which gives a symmetric response you can avoid having the angle of twist. Second is in reinforced concrete. In reinforced concrete it is well known that concrete cracks easily under torsion, okay, and so the torsional stiffness that you get from those formulas, the formulas are for homogeneous elastic materials, have to be factored, and usually we assume a factor of around 15%, 0.15 because it drastically drops to 15%. It is not 0, but some design codes, in fact all design codes allow you to simplify your analysis by assuming it to be 0, which is called a torsionless analysis, torsionless grillage analysis, but it is not exact. If you want to do it exactly, take about 0.15 of the gross properties and do it. So the first instance is in symmetric grid systems as I mentioned, and the advantage is you can reduce the degree of kinematic indeterminacy. Some of the elements, grid elements, you replace with beam elements, but you do all these tricks only when you are dealing with the reduced element stiffness method. Otherwise you pretend, let it work out the values and you will get 0, it is okay, a standard program will do it like that. In reinforced concrete, torsional stiffness can get drastically reduced with the onset of torsional cracking, which is generally inevitable. RC design codes often permit the neglect of secondary torsion or compatibility torsion which is different from primary torsion. There are some torsions you can't avoid. To satisfy equilibrium you have to have them, but in grids you don't have those instances. In such torsionless grillage analysis, we do this grillage analysis frequently in bridge decks. Okay, so there you can release these twisting moments. All the grid elements can be replaced by beam elements. But let's learn the right royal proper way of dealing with torsion, and torsion will always be there. It may not be significant, but you should appropriately assign the torsional stiffness values. So the method is the same as we've done earlier. Let's demonstrate straight away with one problem. So this is a symmetric orthogonal grid floor. Okay, you have full fixity against flexure and torsion at the extreme ends, which is A, B, C, D, E and F. It is assumed that all the grid elements have the same prismatic section. EI is given and GJ is shown as 0.2 times EI. You have a gravity loading uniformly distributed of 30 kilonewton per meter. So straight away you notice there is some symmetry in this system. Okay, you can see that the two shorter beams C, D and EF will behave identically. You can actually cut the system at the middle J, right, and take advantage of symmetry. You can go one step further and you need not have grid elements for all of them. Which can you replace with beam elements? AB? AB, because you can see that DG and GC are going to be acting like mirror images, right. So there can't be a angle of twist along the direction AB vectorially, but CGD can twist. Why can it twist? Because if you take the beam AGJHB, it's going to deflect in an odd way. You are only sure that the slope will be 0 at J because of symmetry, and the slope will be 0 at A and B because the ends are fixed, but anywhere it need not be 0. So it will have a rotation, it will have definitely a rotation at G and H, and what is a flexural rotation for that longitudinal beam will be an angle of twist for the element CD. So if you isolate the element CD, you will have to apply a torque at G, which comes from this integral connection. Is it clear? So you must first visualize the physics of the problem. You can cut the beam at J. What is the boundary condition you will put there? You will put a guided roller because it can deflect, but the slope is 0, so you can fix it against rotation and there is no twist there, right, because it is a point of symmetry. If you show the load, if you write down the degrees of freedom, you will find that you normally would take 3 active degrees of freedom at that common joint G, but you need to take only 2 because we have just established that there is not going to be any rotation along the axis AJ, along the x axis, right, because of symmetry. Is it clear? D, there is no rotation above that axis. Is it clear? Because that would mean twisting of that element at G. Is it clear? So you have to intelligently minimize your work by assigning coordinates carefully. So 1 and 2 are the only, D1 and D2 are the only displacement unknowns. Then at the restraint coordinates, of course you can add all the remaining degrees of freedom. So you have altogether 10 degrees of freedom, 2 of which are active and 8 of which are restrained. Is it clear? I am just demonstrating with one example. So you can make the grid elements, you identify the grid elements, they are the elements one and 2, and the beam elements are 3 and 4. of which 4 can be simplified with 1 degree of freedom. Why? Because you have a guided roller support, we have done that, so you can treat it like a cantilever. Is it clear? So we have made all the simplifications possible to reduce our work. Any questions? 1 and 2 are grid elements because there is going to be torsion in these two elements. 3 and 4 are beam elements. 3 will have 2 degrees of freedom, whereas 4 will have only 1 unknown degree of freedom because of the advantage that you have of the guided fixed support. Okay, so we are really taking advantage of all the knowledge that we have to solve this problem. Okay, so solution procedure is exactly as we have done for all the problems till now. You do not have any support settlements, so the steps are straightforward. We are doing the reduced element stiffness method. So first, this is the simplified model of the grid that we are going to look at. You have to first generate the TD matrix, right? Will you do that? You have global coordinates and you have local coordinates. Can you write down the TD matrix for these elements? And once you do that, everything falls into place. So to do the TD matrix, you have to apply D1 equal to 1 and see what happens to those rotations, then D2 equal to 1, etc. So I have done it here and let us go through it carefully. Okay, listen carefully. D1 equal to 1 means we are giving a vertical displacement here but not allowing any other movement. If this goes up by 1, what do you think will happen to all the different elements? If this goes up by 1, you will have chord rotations, right? You will have chord rotations. Let us take the first element. Will you have an anti-clockwise chord rotation or clockwise? Anti-clockwise, which means you will have clockwise equivalent end moments. So you get minus 1 divided by the span is 5. So 1 by 5 is 0.2. So you get minus 0.2 minus 0.2. Is it clear? And you do not get anything in the third degree of freedom because that corresponds to an angle of twist. So is it clear what we got here? What about the next element? In the next element, it is clockwise if you look at it G to C, right? But we are looking at it from C to G. So the orientation is done this way, so you have to be very careful. You will get it identical. Okay, and what about the element 3? Element 3 also has a span of 5 meters. There also you have an anti-clockwise chord rotation. So does it fall in place? And for element 4 it does not matter because it is a cantilever. You lift it up, the guided roller will also go up, so you do not get anything, 0. Is it clear? So the first column we filled up correctly. The second column corresponds to 2. As far as the elements 1 and 2 are concerned, it is clearly an angle of twist, but it is going to be outward only for element 2 and inward for element 1 by the sign convention we took. So we write here minus 1 and plus 1, right? And as far as the element 3 is concerned, it is a flexural rotation, so it is 1. As far as element 4 is concerned, it is a flexural rotation, it is 1. Like that, can you fill up all the others? Okay, now so you can do this exercise, go through it carefully. We have just demonstrated this. You have to be careful about the chord rotation and the sign conventions. It is quite straightforward. This is the displacement transformation matrix. You are doing it by looking and by inspection and filling it up. Is it clear? Can I proceed? Okay. So next is fixed end forces. Luckily for you, all the beams are having a span of 5 meter and the loading is the same, 30 kilonewton per meter, right? So the fixed end moment is plus or minus 30 into 5 squared by 12, which turns out to be 62.5 kilonewton meter. So if you take the first two elements 1 and 2, it's plus 62.5, minus 62.5 and 0, right, anti-clockwise positive, clockwise negative, 0 because there is no twist, no torsion. And then you can also find the vertical reactions. Similarly for the second element, it's exactly similar, I mean the third element, okay, it has the same span, the same loading. And for the fourth element, it's a guided roller support, so you should take the full span, you will get the same formula, 62.5, it's anti-clockwise, it's positive, and the vertical reaction is also the same. So we are dealing with the same numbers, 62.5 and 75, because all the spans are identical, the loads are identical. Is it clear? Not difficult. Then from this you can also check out your deflection, because that's a question asked, what's the maximum deflection in that entire grid. It's very important when you design grids, because deflection is one of the governing criteria for deciding the depth of the beam. The deflection should be within acceptable limits. Okay, so the fixed end deflection is very easy to work out. You know that for a simply supported beam, the deflection is 5 by 384 WL raised to 4 by EI. If it's fixed it's 1 by 384. So we just use that formula and you get a very small deflection of 0.977 mm in this case. Okay, right. Then you can add up all the vertical reactions and you can find the equivalent force vector. Fa 75 into 4 is 300 kilonewton, it's acting upward, so that's your fixed end force for F1. F2 gets cancelled out because minus 62.5 and plus 62.5 neutralize each other. Similarly you can get the fixed end force vectors at the restraint coordinates, it's easy to compute. Okay, you just pick up those values from your fixed end forces. So you are ready with this. You can find your resultant net load force vector. There is no concentrated load given in the original problem, it's only uniformly distributed load. So you've got your net force vector exactly as we've done in earlier problems, Fa minus FFA. Fa is a null vector, FFA we've already computed. So element stiffness matrices are very easy to calculate, you know the formulas, Ei by L is known, Gj by L is known. The first two are grid elements, so you can write K1 star and K2 star, it's a 3 by 3 matrix. The only new item here is the third row and third column. You just put Gj by Ei value, which turns out to be 0.2. You can expand it. For the third element, it's a conventional beam element, remember 4 Ei by L, 4 Ei by L, 2 Ei by L, 2 Ei by L. And for the last element, what will it be? It's going to be 1 by 1. It's going to be 1 by 1. It's a cantilever, right? So what will be the formula? Ei by L, that's it. And L for this is 2.5 meter. So you are ready with all the K matrices. You've got the T matrices, TD matrices. You can. This exercise is best done with the help of maybe MATLAB or something. You can get Ka and you can get Kar, you can get Kra, you can find the inverse of Ka matrix and you use the standard equilibrium equation, find the displacement. Okay, you've got D1 and D2, you got the net load vector, so it's easy to find out. After you found D1 and D2, and you can actually substitute the value of Ei and get the values. Remember D1 is a vertical deflection there, but we want the final deflection, so how do we get that? This deflection D1 has come from yeah, but the other part will give you the same deflection. You have to add something to this. You've already calculated due to fixed end forces what the deflection is. You have to add that. You have to add something else. That rotation in a cantilever will give you some additional, because you've simplified your problem here, will give an additional value. Remember, for a cantilever, at the guided roller support, we are finding the deflection at the guided roller support, not at D1. Please note, we are finding the deflection at J. So at J you get something more than what you get at G. What's the additional thing you get? It's a slope into span by 2, you can prove for a cantilever. So you have to do it very carefully and work out the deflections. Support reactions are easy to calculate, use that formula and take a look at the final free bodies. You will find that in that long beam you will have some local torques coming because of the connections with the shorter beams. So you do this, draw your free bodies, check your equilibrium, find the member end forces by this formula and draw your shear force diagram carefully. We have done grids earlier, so I am going fast. We have done this kind of problem earlier. Draw your bending moment diagrams. You will have jumps in the bending moment diagram where you have local concentrated moments acting, and you will also have twisting moments in the shorter beam. Is it clear? So this is all you need for a design. You have got the full beam, you have got all the internal forces, you have got the support reaction, you have also got the maximum deflection. So it's a very powerful way of solving such problems. This is a problem that is very interesting, but we do not have time to solve it. Please read it in the book. Do not worry, in the exam I am not going to ask you such a problem, but architects like to give such a roof, for example. Okay, you have an octagonal roof and you have got these radial elements and the circular elements. Can you design this from first principles? Well, you can take advantage of symmetry and solve this problem. Okay, you just need to apply your brain. You can actually use some shortcuts and crack this problem very easily. It's a reading assignment for those of you who are interested. Okay, I have given you an assignment problem which is much simpler. Remember this problem? It's a square grid problem. You've got two beams, they are identical, forming a plus shape, but you have an eccentric load acting on one of them at F. So here tell me, and you are actually asked to plot the rough shapes of the shear force, bending moment and twisting moment diagram, which you can by inspection. Now look at this carefully. Which of them will you treat as grid elements? Okay, so if you draw the free bodies, it is similar to the previous problem. You will find that AB will be connected to CD through the joint at E, right, and for one of them, for AB, what do you have? Do you have beam elements or grid elements? Beam elements, right, and for CD you have a grid element. So it's similar to the other problem. Please try to predict the shapes of the bending moment and shear force diagram, and then with these notations you can go ahead and solve the problem, right. This is the last problem in your assignment which you should complete soon. And now it's time to look at your second quiz results. I've got the paper, so take a look. Okay, here the degree of kinematic indeterminacy is 2. Okay, so we are looking at your quiz questions which you did. I am happy to say that some of you got full marks, 15 out of 15, and I am sorry to say that we have a full spectrum. Some of you got very low marks. So please figure out where you went wrong, if you went wrong, and go through it carefully. It's very clear that some of you are fully understanding what's happening, but some are not. I've been liberal in my marking, but take a look at this. You remember that such problems can be solved very easily if you take advantage of anti-symmetry, but some of you insisted on slogging the hard way, 3 unknown displacements, and you got it right also, but it's so much of effort, you're not really taking advantage. It's actually a very easy problem. You remember we've done this earlier. You can reduce the problem to superposition of symmetric and anti-symmetric components. Yes, we have done this, and you need to analyze only one part of it, because the other part does not give you any curvatures. So that is all you need to analyze, and you have to find fixed end moments correctly and write your slope deflection equations correctly. The fixed end moment is 30 into 4 by 2, 60, right, anti-clockwise. This is conventional slope deflection method, so you put minus because it is anti-clockwise, and it is EI by L because it is cantilever behavior for the element AB, and it is 3 EI by L. L in this case is 3 meters, right. Some of you did it by memory based on the problem we solved earlier, so I do not know, you have phenomenal memory because you put a value of 2 EI for the beam element, because in the problem we did in here it was 2 EI. It's very the Indian memory is very good, but unfortunately you are not seeing the problem here. EI is constant, and so that is a change you make, and if you solve this, do the equilibrium, it's very easy to solve. Your deflection diagram, your bending moment diagram should look like this. Okay, it's an easy problem. Next problem. Next problem was actually a easy problem. Some of you try to figure out what truss shape it could be and did all kinds of funny things, but it's actually very simple. So if you go back to basics, remember this picture. You have the structure level coordinates, you have the element level coordinates, you have TD flowing downward from D to D star, and you have TF flowing downward from F to F star. Remember, the left one corresponds to the flexibility formulation, the right one corresponds to the displacement formulation. In this question, what is given to you? You have got TD and you have got F, and what are you required to find? F star. So you have to just use the right principles. You have TD and TD is flowing downward, but you can bring in the contra gradient principle, which gives you TD transpose, but which gives you a connection between F star and F, but you need to go the other way. So what should you do? Invert it, okay, and you get the answer. Now I have got all kinds of permutations and combinations from you. Some of you just multiplied the same TD matrix and hoped that you get the forces, which is ridiculous. Some of you took a transpose because you knew there was some contra gradient principle involved, and you multiplied and you got again some ridiculous result. But many of you did it right. You have to invert it and do it, and you do not need to figure out what truss is involved. It is a very simple problem. Okay. Third question. This we have done earlier, so you should have cracked this. First of all, try to minimize your work. Those you need to realize you need to find only KAA and delta FFA because there is nothing else involved. So what is the size of KAA matrix? 1 by 1. So you really do not need to even bother about the restraint coordinates. You could have managed with 1, but okay, since all of you, in fact there is no one who took only 1 coordinate, so let me also follow your example. This is a familiar picture. If you want the full TD matrix, you can write it down, but all you need is only TDA, and your K star matrix is very simple. It's a diagonal matrix. So your KA is child's play. In one shot you can get it. Don't get the full K, but almost all of you got the full 3 by 3 K, and then you picked up the top left hand corner and said that's KA. You needn't do all that. It's very easy. See, when you write an exam, you have to really be intelligent and do the correct thing in the least time involved. Okay. So what about your fixed end forces? Some of you forgot that only one bar is heated. You kind of heated both the bars and you got it wrong. So it's very easy to solve. Okay, the answer is 12 mm. Moving on the right side, some of you moved it on the left side and never thought that it's foolish, because if you heat that bar, B is going to move to the right. How can it move to the left? Last problem, again simple, it's a truss. All you needed to do was to generate the stiffness matrix, nothing more. So it's just multiplying some matrices. This is the problem. You know how to write the TD matrix. It will look like that. You have 4 elements. Don't forget the spring is also an axial element. So it's very easy to write down. It's a 4×3 matrix. Your K star matrix is child's play. Remember, everything is given to you. The actual stiffness is 40 kilonewton per meter, but some of you thought it is EA and you divided it by the span. I don't know why. So you've got this kilonewton per millimeter. You multiply it out, you get the final answer. Okay. Thank you.